So today, first we will discuss uh, about deformation tracts. So definition. So we have already discussed about uh, uh, inclusion map having uh, left inverse, inclusion map having left homotopy inverse, and inclusion map having right homotopy inverse. Also, we have discussed that inclusion map cannot have right inverse. Next, we'll discuss about inclusion map being equivalence, right? So, a subspace A of a topological space called space is said to be said to be a weak deformation retract of X if the inclusion map I A X is a homotopy equivalence. We have following lemma. A is a weak deformation retract of X if A is a weak retract of X and X is deformable in A. X is deformable into. So proof is simple by using previous results. Uh, so A is a big deformation retract. A is big deformation retract of X if and only if uh, this inclusion map is a homotopy equivalence. Now, uh, inclusion map is a homotopy equivalent, means it has a homotopy inverse. Equivalence when only if there exists f from x to a such that uh, I compose f is homotopic to I a and f composed I is homotopic to I x. Right? Now, from here you see I has a left homotopy inverse which is f, right? But if inclusion map has a left homotopy inverse, then uh, A is called B retract of X. And if we have seen that if we have seen that X is deformable into A if and only if inclusion map has a right homotopy inverse. So we have both the things. So A is a weak retract of this implies that A is a weak retract of X and X is deformable into A. Now, if we assume that X A is a big retract of X and X is deformable into A, then what will happen if A is a big retract of X, then inclusion map I is going to have a left homotopy inverse, that is this. If X is deformable into A, so this is equivalent to inclusion map having right homotopy inverse. So, right. Now this F1 and F2 in general, they may not be same, right? Because if if A is a big retract of X, then I is going to have some right homotopy inverse, left homotopy inverse. So B, suppose that is F1. And if X is deformable into A, then it means that A inclusion map has a right homotopy inverse. That is, there is some F2 such that this is there. Now, it means F1 is a right homotopy inverse of I and F2 is a, F1 is a left homotopy inverse of I and F2 is a right homotopy inverse of I. So we have already seen that if given any morphism, if it has left as well as right inverse, then uh, uh, they will be equal. The left and right inverses will be equal. So this what we can write here, F1 class I class equal to IE plus and FI class F2 IX class of this This implies that this F1 class of F1, it means what? F1 is inverse, left inverse of this, and F2 is right inverse of this, but then left and right inverses will be same. Right, so it means that there is a this inclusion map has a uh, uh, inclusion map is a homotopy equivalence. So this completes the proof. Next, there are some other variations of this big deformation retract. So that is basically some stronger versions of this idea. So a subspace is said to be strong deformation retract of X if there is a retraction R from X to A such that such that uh, this relative to A and no, so this is actually this is not required. This so R composed I is homotopic to IX identity on X relative to A. Of course, because R is a retraction, I composed R is basically this is already there. So this is the condition that R composed I is homotopic to IX relative to A. Basically, what it says means that uh, uh, a subspace A is a strong deformation retract of X if there is a retraction R from X to A such that this Uh, R is a right homotopy inverse uh, relative to A. So if uh, F is a homotopy from Ix to I composed R relative to A, then F is called strong deformation. Then F is called strong deformation, deformation, retraction of X into A. Also, there is an intermediate concept of so we have defined big deformation retract, strong deformation retract. There is another concept, just deformation retract. So definition: a subspace A is said to be a deformation retract of a space X if there is a retraction R from X to A such that such that uh, R composed I is homotopic to Ix. So that relative to A condition is not there. Yeah. Generally, if F is the homotopy from uh, X, then F is called deformation retraction of X into A. So you can see that every strong deformation retract is also a deformation retract, and every deformation retract is also a big deformation retract. So we have here strong deformation retract implies deformation retract, deformation implies big deformation retract. So there is a result We have following lemma. If X is deformable into if X is deformable into a retract, then to a retract A, then A is a deformation retract of X. Deformation retract of X. So proof is simple. It is just observation. So if X is deformable into a retract A, right? It means that A is yeah. So yeah. So it means that A is a retract of X and X is deformable into A. Now we have seen that X is deformable into A if and only if X has a if and only if inclusion map of A into X has a right homotopy inverse. So, so proof is obvious. Proof is obvious because if X is deformable into A, it means we have already done that. It is equivalent to saying that inclusion map from A to X has a right homotopy inverse. It is that is I composed sorry F composed I is homotopic to X, right? Also, uh, if A is a retract of X means what? This there is a retraction X from R from X to A, that is I composed R equal to, right? It means R is so if this is there, then of course this implies what? I composed R is homotopic to I also we can write. It means R is a left homotopy inverse of I and F is a right homotopy inverse of I. But then uh, we can conclude that from here that I F I X and I this R, right? So from this, what we can say, that F is right inverse of this and R is left inverse of this. But we have seen that if you have a morphism which has a right inverse as well as left inverse, then left and right inverse they will be equal. It means what? It means we'll have R equal to F. All right. It means that this it means your R is homotopic F, right? That implies what? R composed I is homotopic to uh, no this one. We are interested in this one. So I compose R is homotopy to I compose F, but this is homotopy to IX. So this is homotopy to IX, right? So by definition of deformation retract, we conclude. Next, we have a result uh, which is quite interesting, but will not go into proof because that will require a bit more detailed study of homotopy that will not be doing because we are interested in mainly in fundamental group, that is the first homotopy group, uh, and for that there are few results from homotopy theory that are required. So we are discussing only those results. So there is a theorem: two spaces x and y have the same homotopy type if and only if they can be embedded they can be embedded as a beak deformation retracts of the same space jet. Proof: if you are interested, you refer to Spinier's book, right? Because but for proof you need a few more concepts, right? So what it says basically, if you have two spaces, right? If they are homotopic, they are of the same homotopy type. If and only if they can be embedded uh, in a bigger space Z, right? I say big deformation retracts of Z. So what is an embedding thing? So basically, an embedding x given any uh, so you can say that x is if x is any space and z is any other space, then x is said to be an embedding. So a map, right? So a map. So here we mean by map, we are talking these things in topological category. So by map we consider continuous function. So a continuous function f from x to z is called an embedding if f is an embedding if f is injective and f from x to fx is a homeomorphism, where this fx, this has a induced topology from Z, right? So basically subspace topology induced from Z, right? Next, let us see some examples. Some examples. First, so we have seen that if we take a convex set is subset, so in Rn, if we take X Rn convex set, then if we take a point x naught in X, then X uh, uh, then this x naught is a strong deformation retract of x. So what was the we defined from I to x by f x comma t equal to uh, x naught plus 1 minus t x, right? So we defined homotopy uh, like this. Then you can see that this f x naught t equal to t x naught plus 1 minus t x naught equal to x naught, right, for every t, and f x1 equal to 1 to x naught plus 1 minus 1 0, that is x naught, right? So this shows that this is a capital F is a strong deformation retraction of capital X into x naught. Next example, see this Sn. Sn. So what is Sn basically? You know that this is x belonging to Rn plus 1 such that norm x is 1. This is how this Sn is defined. So Sn so Sn is a strong deformation retract of Rn plus 1 minus this. If you remove origin 0 from Rn plus 1, then Sn is deformation retract of if we define a map f from Rn plus 1 minus 0 I to Rn plus 1 minus by f xt equal to 1 minus tx plus tx upon norm x in Rn plus 1 minus 0 and ti. So you can see that f xt. So if x is in for x in Rsn, right? Means norm x equal to 1. When norm x equal to 1, what will you have here? This is 1. So you have tx 1 minus tx plus tx. So tx minus tx will cancel. You have x, right? For every x in Sn, you have this, and f x1 equal to, when t equal to 1, you have this 0, and this is x upon norm x, right? So x upon norm x has norm 1, right? So this is this belongs to Sn, right? For every x belonging to Rn plus 1 minus, and yeah, yes, for every t in I. This is true for every t in I. Thus, f is a strong deformation retraction of Rn plus 1 minus 0 to Sn. So we stop here. In the next classes, we'll be discussing some more examples.